just have a couple of quick notes about some of the proofs in Chapter 5. First is in the proof of Theorem 5.1. They're using a technique that you don't normally use in calculus. For instance, we know that, maybe I'll write it correctly, right? d dx from calculus of x squared equals 2x. The way you normally prove that is you say the limit as x goes to x naught of x squared minus x naught over x minus x naught equals the limit of, oh, you can cancel, so you get x plus x naught equals 2x naught. That's normally how you prove it, but what they're doing in this proof of 5.1 is they're using a technique that's very much equivalent. They're going to prove that the limit as x goes to x naught, this is an analogy, of x squared minus x naught over x minus x naught minus 2x naught, they're going to prove that this goes to 0, that this equals 0 actually. So, right, it's conceptually the same thing, except they're doing subtracting it and showing that it goes to 0. In other words, they get to make it small as delta w goes to 0. So that's the basic idea there. And notice, of course, the mechanics of this work out exactly the same as 2x naught equals limit of x minus x naught after you do the subtraction, which is going to equal 0. So these are completely equivalent. In the proof of 5.6, it's a little unclear, in my opinion anyway, it's a little unclear how they get the final answer. And they're just using a couple of basic ideas from analysis. They get that this thing times a big whole mess is what the polynomial is, essentially, the length of it. And then they say, oh, well, so this thing has got to be between 1/2 and 2 times this thing. So what they're doing here is that they're showing that this thing is going to go to 1, which should be clear. But what they're actually doing is they're saying if r is big enough, they're saying that this whole big mess is going to be trapped between 1/2 and 3/2. So they're saying it's going to 1, which means if r is big enough, it's going to be trapped between 1/2 and 3/2. So it's going to be at most 1/2 away from the number 1. So that's where the 1/2 comes from. And because 3/2 is kind of ugly to work with, they just say, oh, if it's less than 3/2, it's got to be less than 2 too. So that's where the two constants come from. So if you're familiar with analysis, you might want to say that they're using an epsilon is equal to 1/2, and then they're actually just taking a bigger epsilon slightly to make the number a little bit nicer. Okay, finally, in the proof of 5.16, they're talking about well-defined functions. They have this function, let me just find it. F is equal to gamma z of f, I believe is what they do. Yeah, and why is this well-defined? Well, well-defined means that there's only one possible answer for f. It could be, if you define things poorly, that there might be two possible ways, and it might depend on the path. So let's assume that here's the point z, and here's the point z naught. And let's assume that we have two different paths. So let's suppose that this path goes like that, and that path goes like that. How do we know that they're the same? So the value of capital F is equal to the integral along that path, and it's also equal to the integral along this path, the green path. We have no idea that they're the same. But we do know that all closed loops end up integrating to 0. And notice that if we tweak this slightly, if we go the opposite way, we get a closed loop. So in other words, if we get, let's see, the integral of the red minus the integral of the green should end up equaling 0, which means that they're equal. And they're done. That's well defined.